Okay. Today we have to finish talking about lines and also planes, which I haven't told you about. Um, so let me just remind you, I said about lines. Uh, okay, so here's like the idea of how you should think about a line is that a line is, and this is something we'll use more on Monday, is that a line is kind of like the trajectory of a particle that moves at constant velocity. That's the best way to think about a line. So in practice, what that means is that, to specify a line, what you need is a point which you think of the initial point. Okay, I'll call that P naught. So let's call that X naught, Y naught, Z naught. Okay. So this is just a point on the line, which you can think of like the point that you are in at time zero. You one. And also for a line, you need like a direction. So the direction for us is given by a vector. So I can draw the vector somewhere in here to make it more clear. So I have this vector V. Okay. I have this vector V, and so it has three entries, V1, V2, V3. Okay. Let's check this. And then so this is the direction of the line. Okay. And then the equation of the line is that the equation of the line is an equation for any other point on the line. So any other point on the line, you can think of it as x of t, y of t, t of t. Okay. That's what I called last time, like r of t. So that's kind of like the point that you're at time t. So again, if you move along the line with velocity v or in the direction v, as time goes by, like you will just be at different locations on the line. And so at time t, this is where you would be at. And so the equation of the line is that, your position at time t is your initial position. Let's call that r naught actually. Is your initial position plus t times the velocity vector. So you just move along the velocity vector. And that's kind of like the vector version of what the equation of the line is. Another version that's convenient. So let me just write this somewhere here. So this is called the vector equation of the line. An equation between vectors is an equation between its entries. So you can think of this as three different equations, one for x of t, y of t, and z of t. So this is like the same as like what's called the parametric equations. Which you know that is what you get by decomposing this. So that's just saying like the initial, like, the x coordinate at time t is the initial x coordinate plus how much you move in the x direction, basically. The y coordinate at time t is the initial y coordinate by how much you move in the y direction and so on for the same goes for z. So if you remember what I plotted for you on GeoGebra, the line, this is usually more convenient for like, computational purposes, like because typically the equations, how you would enter it on the computer is just like for each entry, not like as a vector. So that's why it is common to ask for the parametric equations, but it's really secret. I mean, it is really the same as the first one. It's just like a more explicit way of writing them. Uh, Okay, and in fact, what we'll start doing next time, this is calc 1, right? This is a function of a single variable, right? T. It's just that you have three functions, right? But these are functions that depend on t. So if you take for example, if you take the derivative of x with respect to t, you get v1, right? So that matches the idea that the derivative is kind of like the velocity, like the v1 is the velocity. So what we want to say next time is something like, we want to say next time something like dx dt equals v1, right? And dy dt equals v2, and dz dt equals v3. Okay? Um, if you take the derivative with respect to t. And that's essentially what will happen. So like, well, you see is like to take derivatives of things that depend on time or on t is essentially like the same way which you took derivatives in calc 1. It's just that you have to take more like, there are now like more functions to worry about because like you have x coordinate, y coordinate, z coordinate. You know, so it's just 3 times the amount of work, but each piece is kind of like the same thing as before. And if you took like the second derivative with respect to time, right, like they'll become 0 because these are constants. So that's kind of like saying that, there's no acceleration or that there's no concavity. If you think of the second derivative as concavity, so that tells you how much the curve is bent, but like a line is not bent. So that matches. Yep.
So is the output of a vector equation is a vector?
Yes.
So like our vector R of t is like just the qualities of vector R.
So, right, like RFT, so in terms of like the picture, RFT, if you were to draw it here, would be this vector. Uh, if you prefer, you could write it as x of t I plus y of t j plus c of t k, right? Is that making sense?
Yes.
So because everything is in terms of ijk on both sides of the equation, like then you kind of like you get three equations, like one like for the things in front of I, the second equation for the things in front of j, and the third equation for the things in front of k, if that makes sense. So it is a vector. So like kind of like the philosophy is like a vector equation is secretly regular three regular equations, like for us, because like everything is for us in terms of ij and k. So whenever you write like a vector equation, you're really secretly writing three equations, which is what I'm writing explicitly here, like in terms of ordinary functions. If that makes sense. Anyone else? Any other questions? Okay, so for about lines, there's not much that we need to do like in terms of problems, because our objective is just kind of like to find the equations of tangent lines. Eventually, when we talk about more general curves, the only typical problem involving lines is just how to intersect them. So let me just do like a quick example about that before moving to the next topic, which is planes. So intersection of lines. The only thing here is that there's like a subtle point, which is what I want to mention when you intersect lines. Um, So, what I'm giving you here is like two equations of lines. Let's say I'll just draw them some like. In, just like in a random way, so you have like a line one here. Which is the red one, and then you have a second line, which is the green one, so. Well, basically from the picture, it looks like as if the lines intersect, right? And that's kind of what we're after, finding the point of intersection. So there should be like a point of intersection here. And we want to know what that is, okay? So this is like a typical, I mean, for the line problems, either you're given the equations of the lines as in here, or you're asked to find the equations of the lines, like, but then like you're given like the point and the direction is one way or another. So those are like the two types of problems that you'll see involving lines. For as of now, there are a few more things that you can do once we have planes. But for now, like really, the most important thing is kind of intersecting lines. Okay, so what does it mean? You just have to think a bit about what this means. Like, what does it mean for a point to be in the intersection of the line? Yeah,
The X about
correct. Good. So yeah, if a point is in the intersection of the lines, then that means that it satisfies both equations at the same time. So the the value for x on this side should be the value for x on this side, and so on. So good. So the intersection means that the x, y, and z values are the same for both lines. So x, y, z values must be the same. So that gives you what you call a system of equations. So what is the x value? Is 2 minus, let me write them here. So I'm just copying again the okay, so that is what you get by equating the x, y, z, but there is something a bit subtle, because if I just write it that way, then I am doing, it's almost correct, but there's something that needs to be fixed. There's like an implicit assumption that I'm making here that is not quite accurate, like you just equate the equations like that way. Yeah.
The T's be different.
Right. So the T's could be different, like, if you think about it, geometrically or like pictorially, like, well, let me draw like a very poor card. So, what does like this means? Like, it means like you're traveling along this line and this is your position as a function of time. So it could be like, it's completely plausible that, just to put numbers into like what is going on. It could be that like from wherever you started on the line, maybe it takes you 5 hours to get here, right? So like your T could be 5 hours, for example. But then like, the other person or the other car could start somewhere entirely different, like point on the line, right? Maybe this other one starts here. Again, not the best cars in the world, but, and then like, maybe if for that car, it takes like 7 hours or 2 hours. In fact, it could even take minus 2 hours, because that just means that it happened in their past. So I'm just saying, like, it is like, since you start at first you are on different lines and you can start anywhere on the line. So it's not, you're not forced to kind of like take the same amount of time to get to that point. So mathematically, that means what you were saying, that like the T's do not need to coincide. So that's like the reason why I wanted to do this example. So like what's important here is that the T's are allowed to be different. The T's can be different. And then like, I mean, there's an easy fix for that. Like you could just call one T1. And then you just call the other one T2. So really, like, you're solving this system of equations, but with two different times. Because t here just means like how much time it takes you to reach a particular point. So yeah, like different, along different lines, it can take you different times to get to the same common point. Is that making sense? Makes sense? No. And once you do that, then this is really like well, like an ordinary problem about solving systems of equations. So there's nothing too like fancy that you have to do here. You have three equations. You know, if you have taken linear algebra, they're kind of like more elegant ways to solve this. But essentially, you can just do like a naive substitution and like be done with it. So for example, you can start with your preferred equation, that's fine. So let's start with equation 3, and like from equation 3, if I wanted, I could solve for T1, for example. Like again, because it's kind of like arbitrary where you start. So from equation 3, you get that T1, you get a formula for T1, which is 8 plus 3 T2, minus 1. Okay, so when I send the one to the other side, you just get 7, right? And then what you do after you got to that point is just like substitute into the other equations. So what I'll explain this in a moment, but here, so what I'm going to do is substitute T1, this T1 in 1 and 2. So let's just see what happens if you do the substitution in 1. You get 2 minus T1, so you get 2 minus 7 plus 3 T2 equals 5 plus 2 T2. Okay, so what does that give you? It gives you 2 minus 7, that gives you negative 5, minus 3 T2 equals 5 plus 2 T2. So if you move this 5 to the other side, you get negative 3 equals 5 T2. And so T2 is like negative 2 here. Right? Let me see, just check. Yeah. So that's what you get for T2 according to the first equation. And then you could say, oh, maybe I'm just done with this. But this is where you have to be careful. You actually need to still solve for in the second equation, because we do need to make sure that the system is what's called consistent, meaning that we do get the same answer for T2 according to both equations. So what happens if you plug T1 into equation 2, you get 3 T1, so you get 3 times 7 plus 3 T2 equals 1 minus T2. And so that means 21 plus 9 T2 equals 1 minus T2. So yeah, like that's just 20. Oh, let's put it like 10 T2 equals like negative 20. So T2 equals negative 10. Okay, sorry, negative 2. So that means that regardless of the equation that you used, you got the same value for T2, and that's what we are after. So that means that the system is consistent. Since we got the same value for T2. So what would have happened if we had obtained different values for T2? That just means that the lines actually didn't intersect. There's no way to solve this system. Like you get contradictory information. So otherwise, like say if this one had given you T2 equals 1 and this one T2 equals 3, that means that like the system couldn't be solved. So otherwise, if the T2s were different, if the T2s had been different, that means that the lines didn't intersect. So like the picture would have been misleading, that's what I'm trying to say. And once you have the same value for T2, like what is T1? Well, T1 is just 7 plus 3 T2, but it doesn't matter which value of T2 you use because the point is that they're exactly the same. So you get 7 minus 6. So that's 1. So that means that T1 equals 1. Okay, so those are the times. So that means that after 1 hour, the first car, the red one, passed through this point, and 2 hours in the past, the other one had passed through that point. And the point of intersection would be. And so what is the point of intersection? It's basically what you get by plugging like. You plug the values of T1 or T2 in the corresponding line equations. So you get X, Y, Z, for example, 2 minus T1, 3 T1, 1 plus T1. So that gives you 1, 3, 2. Is that okay? Well, let me give you a second to copy this. Is that making sense? So you could have used, like, if you also had plugged T2 equals -2 into the second equation, you would also find 1, 3, 2, because exactly this was set up so that they would give you the same X, Y, Z values. So the important thing about this problem to point out is that the T's need to be different here. So the first thing to be aware of is that the T should be different. And the second thing is that you do have to check that the remaining equations give you this agree on the value for the other variable. Otherwise, like the system wouldn't have been consistent. So those are the two main things that you have to check for when you're like intersecting lines.
Is it possible for like the T1 and the T2s to solve correctly, but it's still not consistent?
So if they solve correctly, as in like all the equations agree on the values, then it definitely, there's a solution. Yes, yeah. So the only, again, it kind of like the way we're doing it, it looks a little bit. There are better ways of doing this where it looks more explicit, but the thing is like, at the end, if you had found like, different yeah, like what happens, like, if you said it in a different way, that like the inconsistency is more clear because literally you get something like stupid, like 0 equals 1 or something of that sort. But in this case, yeah, as like once you solve for one of the variables and plug it into the other two equations, if those two other equations give you the same value, then the system can be solved, then there's an intersection between the lines and everything works fine. And then you don't have to worry about anything else. Okay, so the other thing that I have to tell you today is like the equation of a plane, and that's actually not kind of fun to find, but it's. Now we're talking about planes. So what is a plane? So a plane for us is literally like an infinite piece of paper, right? So it's like an infinite sheet. So just think about this, something like this that extends in all directions. So you have, like, again, like our goal is how do you have to think a bit more geometrically first. So the question is like, how do you specify a plane geometrically in space. So there are a couple of alternatives, but for example, one thing you could think of is like, maybe to specify a plane, I want to specify kind of vectors that give you the direction along the plane, right? So like kind of like the vectors that I'm drawing here. But if you look at what I'm doing right now, there are kind of too many options of vectors like here, like the plane, like there are multiple directions that you can draw on a plane. So that is okay, but it's kind of like too open-ended for us. So instead of like choosing a vectors that are kind of like in the direction of the plane, what's more convenient for planes is to choose a vector that's perpendicular to the plane. There's less ambiguity on how that works, because if a vector is perpendicular to the plane, what other vectors could be perpendicular to that plane? Well, you could rescale that vector, right? Or you could turn it upside down, but except that's more or less the only thing that can change, so all the vectors are perpendicular to a plane are more or less parallel to one another. So that's why this is a better answer than just like having like the vectors on the plane, which you can just like kind of rotate around and don't relate them in any particular way. So what I'm trying to say is that to specify a plane, what we're going to ask for is kind of like a vector perpendicular to it. This is called the normal vector, so I'll write that down in a moment. Okay, and so once you know the normal vector, you kind of know like how the plane is tilted with respect to the floor, okay? But still, like, there are many planes that have the same normal vector. So for example, think of the plane here, if I start moving this iPad like up and down, right, they still have the same normal vector, right? So in addition to the normal vector, you still need to tell me a point that the plane passes through. So you need a normal vector and a point the plane passes through, and that is enough. Once you know a point, like you have to put like the tablet somewhere in passing through that point, and then the normal vector kind of orients the tablet so that it's perpendicular to it. So let me write that down. A plane looks like that. So what I'm saying is that we need to think to write the equation of the plane. A vector perpendicular to it. So that's going to be called the normal vector. And let me draw it here. Usually it's called n, so and called the normal vector. So this is a vector perpendicular to the plane. Okay. And you also need a point, which you can call like P naught. I'll also call it P naught. So let me see if I can emphasize that the plane is kind of this piece of paper. So there's like there's a 90-degree angle between the vector and the plane. And the other thing that you need here is point P naught. Okay, so P naught is a point that plane passes through. Is it okay? Does that make sense? Okay, and so my claim is that with that, it's enough. That's enough information to describe any other point on the plane. So let me draw the picture again without like coloring it, make it a bit more clear. So. So you had like, so you had this normal vector. Let's say you had the point P naught here, I'll put it, move it around a little bit so that it's a bit more clear what's going to happen next. Okay, and then, you have the point P. So P is any other point on the plane. So let me specify that. P is any other point on the plane. So, once you have once you have the 2 points, those 2 points on the plane, what you can do is, for example, you can draw the vector P naught P, okay? So if you remember from last time, this is like the vector that goes from P naught to P. So this is like the vector from. And so let me draw it for you on the iPad. So what I'm saying is that you have a vector in the plane, which is here, right? Sorry, you have a point on the plane, which is here. You have another point on the plane, which is here, right? So I'm connecting these two with the vector P naught P, right, which is what you see here. And so now I'm asking you, what's the relation? Essentially, the equation of the plane is kind of, what it tells you is what's the relation between these vectors that I just drew on the tablet and the normal vector. So what can you say about those two vectors? What looks like in this picture should be, yeah.
That part is zero.
Well, right, like they should be perpendicular, right? Like that's almost by definition of what it means to be normal vector. That when you do this drawing, like they should be perpendicular. So essentially, the plane equation is just that. So the plane equation is just saying that. So the plane equation is basically the statement that P naught P should be perpendicular to N. But we'll write that in terms of a dot product. So it's just that N dot P naught P equals 0. Okay, we're here, just as a remark, because I'm about to show you how this looks. Okay, so this is clearly the plane equation, but it looks a little bit like not super concrete. So to make it more concrete, what you do, well, to make it more explicit, what you write is P as X, Y, Z. To make it more explicit. Okay. So. So that is a plane equation. So let me do an example first to show you how it looks more, how it actually is a bit more concrete than this. But for that, you kind of have to work it out a bit. So, so let me do an example and then I'll tell you like a way that can make it look more explicit. So. So let's say that this is like the point, 1, 2, 5. So I want the plane. So this is my P naught. So I want a plane that passes through that point and has normal vector, let's say, I'll give the normal vector just something. Okay, so we're going to find the plane. So we're going to find the equation of the plane. Okay, so what is that? What is the equation of the plane? Well, it's just n dot p naught p equals 0. Let me put this in yellow still. So what is n in this case? Is 3, -1, 4. And what is P naught P? Well, do you remember like the formula? I just subtracted the entries of the points. So the entries of the points are, I told you call the point P X, Y, Z. So let's call the point P X, Y, Z here. Because we don't know what that is, like it could be any other point on the plane. So since we don't know what the entries are, just call it X, Y, Z. So you get X, Y, Z minus P naught, and P naught is 1, 2, 5. So that's what P naught P becomes. And so what you're saying is that the dot product between these two things should be 0. Okay, so before doing the dot product, if you want, you can just subtract the points. That's kind of more convenient. So, okay, this is easy. It's just X minus 1, Y minus 2, Z minus 5 equals 0. And what is that equal to? That's like 3 times X minus 1 minus Y minus 2 plus 4 Z minus 5 equals 0. Which if you want, you can write in a different slightly, I mean, so this, actually, this is already the equation of the plane. So this is like the equation of the plane. But you can also simplify it a little bit because this is the same as 3x minus 3 minus y plus 2 plus 4z minus 20 equals 0. So what does that become? It becomes 3x minus y plus 4z. So I'm putting like all the variables appearing first. And so that gives you minus 3 plus 2 is -1. So -1 with this one becomes -21. So you can write it as in this way as well. So any of these two versions would be the equation of the plane. So what this is saying is that the plane consists of all the points x, y, z with the property that 3x minus y plus 4z equals 21. So for example, oh, before I continue this, like, is it making sense how I'm getting this information? So for example, So how do you use this equation in practice? So imagine if I asked you like, if zero. So imagine if I gave you the point 0, -21, 0, is that on the plane? Yes or no? It is on the plane because if you put x equals 0, z equals 0, right? And then multiply minus 21, you get 21 equals 21, right? So this one satisfies the plane equation. This point satisfies the plane equation. Right, but if you put something like, let's put something easy. So you put something like 1, 1, 1, right? What happens if you put 1, comma 1, comma 1? So you do 3, 1, that's 3, minus 1, that's 2, plus 4, that's 6, right? And 6 is not 21. So this one does not satisfy the plane equation, so that means that that point is outside the plane. That making sense? So in general, like the way in which you use that equation is that if you wanted to know if a particular point is on the plane, you literally just plug in the values of x, y, z of that point and just check whether the equation holds. So in practice, and maybe let me show you how this plane looks like. So sorry about that. I'll show you. Oops. Oh, let's go to GeoGebra. So again, here, let me erase this plane because otherwise it will get confusing. So I had a point which is 1, 2, 5, right? And then the equation for the plane was 3x minus y plus 4z equals 21. So that is how the plane looks like. So if you look at this plane, like you see, it's passing through this point, which is what we wanted. And yeah, if you could find the normal vector, you would see it's like parallel, or it is like 3, -1, 4. Okay, so in general, that's how the plane looks like. And in fact, like a more like a faster way to, you know, if you look at this equation, you know, 3, -1, 4 are exactly the coefficients of the normal vector, and that more or less is true in general. So in the plane equation, the numbers multiplying x, y, and z are the entries of the normal vector. So let me write that down because that's the other thing that's important about planes that I should tell you. Um, so if you have a plane, that has normal vector with entries a, b, c, and the point on the plane is p naught equals x naught, y naught, z naught, right? Then what is the equation of the plane? Another way to write the equation of the plane is as so is something like this. It's a times x minus x naught plus b times y minus y naught plus C times Z minus Z naught equals 0. So in other words, ABC, so in general, like so the coefficients that multiply X, Y, and Z are the entries of the normal vector. So this is like a more common way of writing the plane equation. And the coefficients. Applying point Z are the entries of the normal vector.
That's pretty much what you just did though, right?
Right, it's just like, yeah, I'm just putting it like in general, but it's exactly that, yeah, it's like just like working out explicitly what n dot p naught p is equal to, right? But yeah, so it's just like saying, it's just like usually like, when you read it, written down, it's kind of written down like this, not like n dot p naught p equals 0, but it's really the same, so, but it's kind of worth pointing out explicitly, so. But yeah, like the point, like, the thing is like, if I get like, think about the problem in reverse. So if I got told you, oh, this is the plane equation, what is the normal vector? Then you can just immediately say the normal vector is 3, -1, 4. So the normal vector can be extracted from the plane directly. That's the idea. Is that okay? Yeah.
You can also form a plane with 3 lines that aren't collinear, right? So-
Right, yes. That actually was my next step, but yeah, good. So, well, in fact, you only need, I mean, you need 2 lines. You don't need 3. It suffices to have 2 because, but yeah, let me write that down. Good. So, yes, let's talk about other ways to form planes, which is what you were asking me about. So essentially, here's another way to make a plane. You have 3 points. Again, it's kind of easier to draw the plane first. So now imagine that you have 3 points P, Q, and R. I have 3 points P, Q, and R. This is a kind of like the analog of 2 points determining a line, right? Basically, the idea here is like essentially 3 points determine a plane unless the 3 points are on the same line, but that's kind of silly. So like just in general, like if you have 3 random points in space, like they will determine a plane, right? So what do we need, what would we need to determine the plane? Remember, a plane is 2 things. A point, we have 3 to choose from, so that we're good on, right? So in addition to the point, we need the normal vector, right? So the only question is like, how do you get the normal vector from 3 points on the plane? It all boils down to that. So how could you get the normal vector?
Like the cross product of, like, you considered like vectors in between the points.
Correct, good. So that's it. So perfect. So there are many like, well, with 3 points, you can draw like a couple of vectors, but for example, I could draw the vector PQ. I could draw the vector PR, okay? I only need 2 of the 3, so like these 2 work. And then, yeah, you take the normal vector to be the cross product and then you're done, okay? So take and to be PQ cross PR, and then that's it. You could also have used RQ. I mean, there are a couple of choices, but they all essentially give you the same plane equation. And that is it. Okay, so this is like how to build a plane from 3 points, right? If your initial data is 3 points, this is how you can build a plane. And then another analogous problem, which is essentially the same, is that imagine that I had 2 lines that like, well, let's say that they intersect just to make it easier. So this is like the way to build it from two lines. Two intersecting lines. So I have line one here. And I have line two here. And well, it's more or less the same as in the previous picture, right? Like each line has its own direction vector, right? Each line, the point of having a line is that each has like a direction vector. So let's call them V1 and V2. And let's see if I can draw them here. Right? So those are the directions of the lines. And it's because of the same reason that you can just take n to be the cross product of, it's just a psychologically, I mean, it's more or less the same as this, it's just psychologically, it feels a little bit different. So you can take n to be like the cross product of V1 with V2. And then what's important is that the point can actually be the point of the plane that you choose can be any point on any of these two lines. So it doesn't need to be the point of intersection. So you don't have to waste your time finding the point of intersection. That's the only reason why I want to bring this up explicitly. So the point on the plane needed can be any of the points of the lines. So you don't need to use a point of intersection, which is something like natural to try, but it's just, you just spend a little bit extra time finding the point of intersection. So doesn't need to be. Is that making sense? And okay, so those are kind of like other two ways, you know, to build planes. But essentially, it just is like, how do you find a normal vector? As you can see, like really, usually finding the normal vector is like the more interesting part on the plane problems. So it's just that if you're giving the data in different ways, like, you know, the normal vector is computed in alternative ways. And the other thing, which is not about finding planes, but just how planes relate to lines. So do I have, oh, I have tons of books. Here's, I have a second plane, right? And here's another plane. So let's intersect them, right? So they just cross one another. What's the line of, what's the intersection? A line, right? So when two planes intersect, you get a line. That's it. What's the condition for two planes to be intersecting? That their normal vectors are non-parallel, basically. So let me write that down. That's a little bit tricky to draw, but I'll try to do it for you. So hopefully it kind of looks piece of paper. So I have a plane one here. Which let's call this N1. So this is the first plane with its normal vector, and this is the second plane with this normal vector, right? So here I have two non-parallel planes. So let's say that I have two non-parallel planes. Intersect on a line. Have an intersection a line. What does it mean for they to be non-parallel? That the normal vectors are not parallel. So N1 and 2 are non-parallel. Yep.
We have the plane equation, how can we get the equation for the normal line from that?
Oh yeah, that's what I'm about to say. So cool. So it's like, let's try to find it more like geometrically. There's different, okay, so one way to do it is like a more algebraic way, which is like the linear algebra way. If you look at the I have done it like that way in previous videos. So if you read when you check the announcement that I'll say at the end of each class, you can check that video and you'll see how I did it more algebraically, but I'm prefer to do it like maybe a bit more geometric today to just show it, because it's a little, kind of, puts more of the concepts we have discussed, at play. So let's think of this as the line of intersection, right? Let's call it L for line. So I want, what do I need to specify the line? I need is direction for the line. So the question is, what is the direction for V for the line? So what is the direction of the line L? Okay, and again, it's kind of convenient to think of the picture like concretely. So okay, if I had more hands, this would be useful. So at this point, so like I'm intersecting the two planes, right? My line is going to be, let's say the line is like, it's shown here like in the orange pointer, right? So this is a line of intersection. So what can we say about this line of intersection? Okay, so what's that? Okay, let's say that this is at a normal vector to the blue plane, right? What is the angle between this normal vector and the line? 90 degrees, right? Because the line belongs to the blue plane, so it should be perpendicular to the normal vector, right? And likewise, here's the normal vector to the second plane, right? What is the angle between that normal vector and the line? It's still 90 degrees by the same logic, right? So because the line belongs to each plane, the direction of the line has to be perpendicular to each normal vector. So let me try to draw it in picture. So what I'm trying to say is that if you have the direction V of the line here, right? This has to be perpendicular, this one has to be perpendicular to the normal vector of the first plane, and also it has to be perpendicular to the normal vector of the second plane. Okay, so we're after a vector that's perpendicular to two vectors that I know. So how can we create a vector that's perpendicular to two vectors that you know? Yeah, just like the cross product. So that's like a nice thing here. So the direction is so direction V is perpendicular to both N1 and N2. So you can take, just to take it as a cross product. So you can take. That making sense? So that gives you the direction of the line, which again, in general, is the most important thing. And then you also, to find the line, you do need like a point on the line. But for that, to find a point on the line, basically what you do is, this one is harder to explain than to do with an example, so I'll just write it first and then just show you the example in a second. So to find a point on the line, you can use, call that point X, Y, Z. And then what you do is make one of the variables 0. Or give a particular value to one of the variables and use the plane equations to find the values of the other two. So give a value to one of the variables. And use use the plane equations to find the other two values. Okay. So it looks a little bit odd, but let me just do it with an example. So let's say the first plane is like x minus y plus z equals 10. So this is plane one. And then the second plane is 2x plus y plus 3z equals 5. Okay? So I have these two planes, the first normal vector. What is the first normal vector of this plane? It's just literally what you get like by copying the coefficient. So it's 1, -1, 1. And what is the normal vector of the second plane? Is what you get by copying those coefficients. These other coefficients is 2, 1, 3. Okay, so what I'm saying is that the direction of the line. So the first thing is that the direction of the line is just the cross product between these two vectors. I'm not going to compute the cross product to just save ourselves some time. And one cross it. So you would do the cross product between those two vectors, that's fine. What I'm trying to explain now is how to find the point on the line. So how do you find the point on the line? Okay, so to find the point on the line, what you can do for like, the point, to find a point on the line, what you can do is like say, well, I want a point whose z coordinate is 0, for example. That's an option. Like, so take z equals 0. Okay. So what happens with the plane equations? Well, because I'm setting z equal to 0, you get x minus y equals 10, and then 2x plus y equals 5. Okay. And then how do you solve this system? It's kind of like the same, like, solve for x and y. So for example, one way to solve for this system is to add the equations. So if you add them, you get 3x equals 15, right? So x equals 5. And once I know that x equals 5, okay, once x equals 5, and then if you plug that in, plug back into the equations, you get, okay, so you get, like, for example, that 5 minus y equals 5, 10, and so you get that y equals -5. So a point on the line would be 5, -5, 0. So that's a point on the line. Did that make sense? So y z equals 0, it didn't have to be 0. Like, for example, maybe you wanted a point with z equals 2. So put z equals 2, and that gives you different values for x and y. So I'm just saying, like, there's a lot of freedom of how to find the point because the line has infinitely many points. So there are many solutions that you could find. But the idea is just to, give your favorite values to X and Y, and then you are done. Does that make sense? Okay, and then, just to finish today, like just for 5 more minutes. Okay, so this is more or less what we need to know about planes. So besides planes, there are other types of equations that are kind of useful. But for now, more or less the only thing that you need to know is kind of like visual recognition of these equations. So let me write down like some that you need. And you'll see next time how we will use them. So here are some other important equations. Okay, so the first one is like the sphere. So here's like the sphere. So it's a sphere at center at x naught, y naught, z naught of radius r. So the equation is just x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. So that's how a sphere looks like. The equation for a sphere looks like. Okay. Again, there's not too much that we'll do with them at the moment, but it's kind of like useful to at least know how to recognize them for now. Okay, let me give you another one to see if you recognize this one. Start with it. I'll start with this this is actually the only version I will use. So what if I put something like x squared plus y squared equals r squared? Okay, so what is that? Yeah. It is a cylinder, it's okay. It's a tricky question because, right, on the xy plane, this is just a circle, right, of radius r, right? But the thing is like there's no z variable. So that means that for each value of z, you get the same circle. So you kind of get copies of the same circle all over along the z axis. So that's how you end up with a cylinder. So actually, because we're working with 3 variables, you should think of an equation like this as a cylinder. So this is like a cylinder. Okay. So again, like you'll see next time, this one will be particularly useful. And there's more that you need to know for now. So instead of like setting x squared plus y squared equals to like a constant right here, r is a constant. Let me set it equal to z. So like the variable z. Okay. So you said
It's like an umbrella.
okay, it is like an umbrella, but let's think why. Because okay, you should think about this as a circle, right? This is like a circle, but now the radius is root of z. Okay, so this is like a circle of radius root of z, which means that the radius depends on the height, right? So as the height increases, the radius of the circle increases. Is that making sense? So when you put kind of like all the circles together, you get like the umbrella or the parabola. This is called like a parabola or like salad bowl. Okay, so this looks like a parabol, this is called like a paraboloid. Is that making sense? So it's kind of like, it's a bunch of circles, but of different radii. Whereas here, there are a bunch of circles of the same radii, because the radius is always r. And like a slight modification of this one, and this is like the last picture I'll do today, is what if x squared plus y squared equals z squared? Okay. So what happens here is still like a circle of radius. Well, root of z squared, so which is the absolute value of z. So it is a radius that still increases with the, well, let's first draw the top part. So it's kind of like a radius that still increases with the height, but the thing is like here, like the increase was kind of goes as the square root. Here, the increase is kind of linear because the absolute value is kind of like z or plus minus c. So it's essentially like it's kind of like still like expanding circles, but like at a linear rate. And so what you get is basically what's called like a cone. Well, if they should look completely symmetric, if that it kind of run out of space. So that gives you a cone. Okay, so you know, maybe the sphere you had seen before. Obviously, you had seen before this as a circle, but now think about it as a cylinder. And these two, it's kind of like good to keep them in mind, which is like this. The first one is a paraboloid, and the other one is a cone. So that is the main shapes, in addition to planes and lines, that you need to know about. But for now, like again, we're not going to do too much with them, except like just know that they are there. So like, you know, there are no specific problems that you need to know how to solve. It's just like, well, next time I'll give you some equations, which involves these things, and then we will intersect them, and we can find some useful things for that. Okay, so let's finish here, and then there are any questions. Okay, so I'll see you on Monday, and then Monday we'll start talking about curves. So this is like the end of chapter 12 for those who are keeping track about the textbook. There's like a silly thing about vector projection that I'll tell you in a bit, like next week, but it's having postponed it because it's not like it's kind of like tangential to the other things like I said, but I didn't want to like derail the topics. So next time we'll do chapter 13, which is I started at chapter 13. Oh, okay.